Up to this point in the previous lectures, we dealt with the distributions which were obtained by grouping observed data. Now we are going to consider distributions that can be expected on the basis of previous experience or theoretical considerations. To illustrate the importance of expected distributions, we have only to consider the proprietor of a shoe store, who must know something about the distribution of the sizes of his potential customers' feet, the executive of a publishing house, who must know something about the distribution of public's literary tastes, or the manager of a restaurant, who must know something about the distribution of people's likes and dislikes for various foods. Unless he knows reasonably well what to expect, the proprietor of the shoe store may stock with shoes which he cannot sell. The executive of publishing house may put out a book which nobody wants to read, and the manager of the restaurant may find himself with a refrigerator full of lamb chops and not enough steaks. In contrast to these three examples, in which the expected distributions have to be based on past experience, there are many situations in which an expected distribution can be based on theoretical considerations. To give an example of the theoretical distribution, let us consider the game of heads or tails, and let us suppose that in order to test whether a coin is balanced, we flipped it 100 times, obtaining 53 heads and 47 tails. Before we can decide whether this coin is balanced, we must know what to expect from a balanced coin. Since the probabilities of getting heads and tails with a balanced coin are both equal to 1/2, it would seem reasonable to say that we expect as many heads as tails, or in other words, the frequency of heads 50 and the frequency of tails again same, the 50, total frequency being 100. It is important that we are using expect in the sense of mathematical expectation, that is, in the sense of an average. The fact that the probabilities for heads and tails are about 1/2 does not imply that we must necessarily always get 50 heads and 50 tails. Sometimes we will get 49 and 51, sometimes 53 and 47, sometimes 40 and 57. But if we repeat this game a great many times, we will on the average get close to 50 heads and 50 tails. In order to convert the distributions of observed and expected number of heads and tails into numerical distributions, we shall refer to tails as 0 for the head, 0 head, and heads as 1 head. We thus count the number of heads observed in each flip of the coin, and we can present the result of our experiment and corresponding expectations as the following numerical distribution. From the experiment, number of heads we have observed in 47 tries. Tails, that is, we have observed 0 heads, and remaining in the 53 tries we have observed heads, 1 head. The corresponding expectations on the assumption of balanced coin, number of heads, for number of heads 0, the expected frequency 50, and for the number of heads 1, again expected frequency 50, 50 to 50. To give a slightly more complicated example of theoretical distribution, let us find the frequencies with which we can expect to get 0, 1, and 2 heads in, say, 120 flips of 2 balanced coins. As we have pointed out before, there are 4 equally likely possibilities, namely tail, 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 head, head, tail, and head, head. Hence, the probability for 0 heads is 0 heads, the case of tail, tail. Its probability is 1/4. The probability of 1 head, that is the cases tail, head, and hail, head, tail, head, tail, and the probability of getting tail, head, or head, tail, or getting a 1 head is equal to 1/2. And the probability for 2 head, 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 is 1/4. We thus expect 0 heads 1/4 of the time, 1 head 1/2 of the time, and 2 heads 1/4 of the times, and the expected distribution for 120 flips of a balanced coin is the expected frequencies are found multiplying the total number of trials, 120, with the probabilities of each outcome of the experiment. The number of heads, the probability of landing not landing any head was 1/4 of 120, which is 30. So, if 3 coins flip simultaneously, there are 8 possible outcomes if the coins are balanced, may be considered as equiprobable. They are shown in the following 3 diagrams. Tail, 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 head, and so on. The frequencies with which we can expect to get zero heads, tail, tail, tail. One head, two heads, and three heads depend, of course, on the total number of flips. In the first example, we considered 100 flips of one coin. In the second, we considered 120 flips of two coins. And the third, we considered 160 flips of the three coins. Here we see the probability distribution of flipping three coins. In order to make theoretical distributions which we have discussed apply to more general problems, we could present the probabilities of getting the different numbers of heads instead of the expected frequencies. The table for one coin could be rewritten as number of heads 0, 1 and the probability of getting 0 heads, 1 over 2 and probability of getting 1 head, 1 over 2. And that for 3 balance coin, 2 balance coin, and for the 3 balance coin, the probability distributions. For the probability distribution of zero heads in Philippine 3 coins, there were 8 possible outcomes. Only one of this sample space matches the case. So 1 over 8, the probability of getting 0 head is 1 over 8. Probability of getting 1 head, 3 over 8, and so on. If we know the probability distribution, we can always find the expected frequencies for any number of flips by multiplying the probabilities by the total number of flips. The last two probability distributions are presented graphically by the histograms of figure 6.1. At the top of the rectangles of the histograms are the frequencies. It should be noted that by drawing the rectangles so that there are no gaps, we are again spreading the classes over a continuous scale. Although the number of heads must be 0, 1, 2, etc. and cannot be 1 over 2 or 3 over 4, the bases of the rectangles go from for the first and for the second distribution, minus 1 over 2 up to 1 over 2, and for the heads 1, the base of the rectangle goes from 1 over 2 up to 1 over 2, and so on. The probability distributions which we studied in the previous section were easy to obtain by enumerating in each case all equiprobable outcomes. To consider a slightly more difficult example, let us now find the probability distribution for getting 0, 1, and 2 sixes in two successive rolls of a balanced die, or in one roll of a pair of dice. Letting S, capital S, and capital N stands for 6 and not a 6 to symbolize the outcomes of the trials. The four possible outcomes are thus SS, SN, NS, and NN, analog to the head, tail, head, and tail, TT for the tosses of two coins. However, whereas HH, HT, TH, and TT were equiprobable, notice that SS, SN, NS, and NN are not equiprobable. Since the probability of rolling a 6 with one die is 1 over 6, the probability of not rolling a 6 is 5 over 6, and since two successive rolls of a die are independent, we can use formula 523, the spatial rule of multiplication for the independent events, and we write probability of not getting a 6 in successive two rolls, that is the probability NN, is 26 over 36. The probability for 2 sixes is 1 over 36, and since Sn and Ns, which both yield 1 6, are mutually exclusive, the probability of getting 1 6 in rolling a dice successively 2 times, that is the probability of Sn or Ns is the sum of probabilities of individual events Sn and Ns. That is the probability of getting 1, 6 in rolling a dice twice. Therefore, we can write it the probability distribution as number of sixes 0, 1, 2 and their probabilities 25 over 36, 10 over 36 and 1 over 36, and the total probability equals, of course, to 1. If we were interested in determining the probability distribution of the number of sixes obtained in 3 rolls of a die, or 1 roll of 3 dice simultaneously, we would have considered the 8 possible outcomes. Since these arrangements of letters S and N, capital S and capital N, are not equiprobable, we shall have to calculate, as before, the probability associated with each possible outcome, using the generalization of multiplication rule to effect that 3 events A, B, and C are independent. The probability that all 3 will occur is the product of the probability of A, the probability of B, and the probability of C. Thus, we find that for each possible outcome of rolling 3 dice simultaneously, the probability of getting n, the probability of getting 1n in rolling a die was 5 over 6. So the probability of getting n is the product of 3 times 5 over 6, which is 125 over 216. Okay. After adding the probabilities of the different arrangements yielding 0, 1, 2, and 3 sixes, respectively, we find the desired probability distribution, which is as follows. The histograms of the two J-shaped distributions of the number of sixes obtained in 2 and 3 rolls of a balanced die are shown in figure 6.2. The process of enumerating The process of enumerating all possible outcomes and calculating the probability associated with each would be rather tedious if we were interested, for example, in determining the probability distribution of the number of sixes obtained in, say, 10 or 20 rolls of a die. For 10 rolls, we would have to consider 1024 different arrangements of the letters S and N. And for 20 rolls, we would have considered over 1,000,000. Although there may be few occasions in which the probabilities connected with 20 rolls of a die are of vital concern, there are many practical problems in which we must know probabilities that are of a similar type. For example, a quality control engineer may want to know the probability of getting 4 defective tubes in a sample of 20 if it is assumed that the sample is taken from a very large lot, in which 1% of the tubes are defective. Or, an election forecaster may want to know the probability of getting a sample in which 12 persons out of 20 are for candidate X, if it is assumed that the probability of any one voter being for candidate X is 70%. In both of these examples, we are interested in the probability that an event will take place a certain number of times out of 20. Of course, there is nothing special about the number 20, which we have used for merely as an example. The quality control engineer might similarly be interested in the probability of getting 6 defective tubes in a sample of 100, and the forecaster might be interested in probability of getting 350 votes for candidate X in a sample of 500. To study this problem in a more general fashion, let us again refer to a game of chance and let us look for the probability of getting 2 sixes in 5 rolls of a balanced die. If we enumerate the 32 possible arrangements of 5 letters S and N, we find 10 of them, namely SS, NN, SN, SNN, SNN, SN, and so on, NNN, SS. Only 10 of 32 possible arrangements of 5 letters contain 2 letters S and 3 letters N, 3 N letters. Making use of a further expansion of formula, that is the multiplication rule, the spatial rule of multiplication for the independent events, to the effect that if they are independent events, the probability that they will all occur is the probability of S intersection S intersection N intersection N and intersection N is equal to 1/6 to power 2 multiplied by 5/6 to the power 3. Thus, we have 10 arrangements. Since 10 arrangements, the probability of getting 2s and 3n in 10 arrangement is the sum of the probabilities of each. Therefore, the resulting probability is 10 times 1/6 to the power 2 times 5/6 to the power 3, and it is simplified as 1250 over 7776, the probability of getting 2s and 3n in 10 arrangements. Let us now investigate the more general problem of finding the probability that a given event will take place exactly x times in n trials. Any one trial is equal to some number p. The probability of referring to the occurrence of the event as a success and its non-occurrence as a failure. We will thus be interested in the probability of x successes in n trials. In order to determine this probability, we could refer to a successive as S with the capital letter S, and a failure as with the capital letter F, and enumerate as before the various arrangements of X letters S and N minus X letters F. Then we could find the probabilities associated with these arrangements, and their sum would give us the desired probability. Probability of getting X successes and N minus X failures. The probability of success is P, and the probability of failures, is the complementary event of success, so its probability is 1 minus P. The multiplication rule gives us this probability in a general form as P to the power X and times 1 minus P to the power N minus X. In this expression, there are X factors of P for the letters S and N minus X factors of 1 minus P for N minus X letter F. Since the probability is the same regardless of the order, we can obtain the desired probability of getting X successes in n tries while multiplying by the total number of distinct ways in which X letters S and n minus X letters F can be arranged. We can finally write the probability of getting X successes in n tries as of, although this formula may look complicated, let us point out that in its derivation, we merely duplicated the steps in which we used earlier to find the probability of getting 2 sixes in 5 rolls of a die. Formula 621 represents a special kind of probability distribution, which is called the binomial distribution. It is a probability distribution because it gives the probabilities of 0, 1, 2, 3, and so on, and finally n successes. If we substitute X as 0, 1, 2, 3, etc. The term binomial derives from the fact that the expression yielded by 6 to 1 for x1, x0, 1, 2, 3, and n are the corresponding terms of the binomial expansion OC. Binomial coefficients the quantities in the parentheses, large parentheses, and x, which are not incidentally not fractions, are called binomial coefficients, and binomial coefficients may be obtained by enumerating all possible arrangements, as we did in the case of the dice, or they may be calculated with the following formula. The binomial expansion of one minus p plus p to the power n. Yes, this symbol stands for the combination operator. The first binomial coefficient is the combination of zero out of n possibilities. I think all we are familiar with binomial coefficients, and it is defined as the combination of x of n as the fraction of n factorial to the x factorial times n minus x factorial. To To illustrate the use of 621 formula 621, let us find the probability of getting 4 heads and 6 tails in 10 flips of a coin. Substituting n as 10 and x as 4 and the probability p as 1 over 2, we obtain the probability of getting 4 success out of 10 trials is approximately 20%. To give an example in which we compute the entire probability distribution, let us suppose that the probability of a person answering a mail questionnaire is 20%, and let us find the probabilities of getting 0, 1, 2, 3, 4, or 5 responses to a questionnaire which is mailed to 5 individuals. Here n is equal to 5, probability is equal to 20%, and the binomial coefficients are 1, 5, 10, 10, 5, 1. Substituting these values together with x equal to 0, 1, 2, 3, 4, and 5 into the formula 621 and rounding the answers to 4 decimals, we obtain 4x0, 4x1, 4x2, x3, and x4, and finally x5. And we can write the distribution of processes as the following table. The probability distribution of responses and its histogram. The distribution, which is also presented graphically in figure 6.3, shows that almost 1/3 of the time, almost 1/3 of the time, 0.33 approximately, we expect to get no response at all. 41% of the time, we expect one response, and so on. And less than 1% of the time, we will get 4 or 5 response. The binomial distribution has many important applications which will be discussed later. Although formula 621 could always give us the necessary probabilities, it is actually seldom used. It would be much too tedious, for example, to use it for finding the probability of getting 5 defective ball bearings in a sample of 400. If the probability that any one ball bearing is defective is 1%. Similarly, it would require an enormous amount of arithmetic to use this formula for finding the probability of getting anywhere from 46 to 54 heads in 100 tosses of a balanced coin. In the last example, we would have to calculate the probability of X success out of n trials for n equal to 100 and probability 1 over 2 and X 46, 47 and 54. Instead of using formula 621, we can either refer to the spatial tables or employ the approximations discussed later. Before we proceed to further problems dealing with the binomial coefficient, let us add a word of caution about its use. Formula 621 applies only if the probability of a success remains constant from trial to trial, and if the trials furthermore independent. The formula cannot be used, therefore, to find the probability that it will rain, say, 25 out of 100 consecutive days. Not only does the probability of rain vary for a period extending over more than 3 months, but the trials are not independent. As we have pointed out in an earlier example, the probability that it will rain in a given day will depend on whether it did or did not rain on the previous day. We had to find the mean of a distribution, the mean of group data constituting a population, as assuming that all values falling into the ith class are equal to the class mark, denoted by xi over bar, class mark. In other words, that the class mark occurs with the frequencies Fi's. If we now divide the n, which appears in the denominator, into the Fi, the formula for the mean can be rewritten as the expression 1 over n should be removed from the formula 631. We took it inside. So the mean is the sum I going from 1 to k, the number of classes of the relative frequency of each class multiplied by the class midpoint or class marks. It should be noted that in this formula, each x bar I is multiplied by the proportion fi over n, namely the relative frequency with which it occurs. In order to define the mean of a probability distribution, we shall substitute for the relative frequencies fi over n with the probability of x bar I, namely the probability is getting x bar I, and we can write it as it in the formula 632. Again, the factor 1 over n should be removed from this formula. To justify this definition, let us remind you that we originally defined probabilities as limit of relative frequencies. In the case of the binomial distribution, x bar I stands for the number of successes 0, 1, 2, 3, and so forth up to n, while the probability P of x bar I is the probability of getting x bar I successes in n trials as given by the formula 621. If we now substitute the probabilities of 621 into 632 and perform certain simplifications, it can be shown that the formula for the mean of binomial distribution reduces to the formula 633, which is the mean of the binomial distribution is the product of the number of trials by the probability of P. This result expressed by this formula should really have been expected. For instance, if a balanced coin is flipped 100 times, we would expect to get on the average 50 heads, and formula 633 yields indeed the mean, the expected value of the binomial variable is 50. Again, 100 times 1 over 2 equal to 50. Similarly, we would expect to get on the average 26s in 120 rolls of a die. Although the derivation of formula 633 is not very difficult, we shall not give it here. It may be derived by substituting the binomial probabilities of 6 to 1 for the probability of xi bar into 632 and performing certain simplifications. Instead of proving the formula for the mean of a binomial distribution, let us merely verify it by considering a special case and calculating in two ways. With formula 632, which defines the mean of probability distribution, and with the formula mu equal to n times p. Using the probability distribution of the number of sixes obtained in 3 rolls of a die displayed earlier, again reproduced here in table 621, we can rewrite it as the number of sixes x bar i's 0, 1, 2, 3 and their probabilities multiplied by their probabilities in the third column for the calculation of expected value of x. So what we did here, okay, again the factor 1 over n should be removed from this formula. Here is the expected value of x, the mean of the binomial distribution, calculated as the mathematical expectation. The total of the product's probabilities by the class marks is 108 divided by 216, which gives us the mean of the binomial distribution as 1 over 2. And this shows that also we can compute the mean of binomial distribution from its definition. 3 times 1 over 6, again 1 over 2. And this shows that the values obtained with the two formulas are identical. Incidentally, this result means that on the average, we can expect to get 0.56s in 3 rolls of a die. Sometimes we will get 0, sometimes 1, sometimes 2, sometimes 3, and on the average 0.5. We had to find the standard deviation of a distribution, the standard deviation of group data constituting a population, as the square root of the sum of the products of class frequencies with the deviations from the mean, squared deviations from the mean divided by n. Again, we can distinguish the relative frequency in the formula. So, of course, assuming again that all values falling into the ith class are equal to the class mark x bar I. If we now substitute for the relative frequencies fi over n with the probabilities p of x bar I of getting x bar I, we can define the standard deviation of probability distribution as the square root of the sum I going from 1 to n probability of xi bar times the square of the deviations of the class marks from the mean. To illustrate the calculation of the standard deviation of a probability distribution, let us again use the distribution of the number of sixes obtained in 3 rolls of a die. Having already shown above that the mean is 1 over 2, we can write, substituting into 3, 6, 3, 6, 3, 4, yields the result. Here, the ordinary way of calculating the standard deviation from the probability distribution table, and from the formula 634 we get the same result. The mean in 300 lives is 150, so the standard deviation of this binomial distribution is 8.66. So it's 66. We introduced earlier the standard deviation as a measure of variation, and sigma equal to square root of n times p times 1 minus p tells us indeed how much variation there is due to chance in the number of successes we might obtain in n tries. To give some idea about a possible application of this formula for sigma, Let us repeat that we said before. Let us repeat what we said before. For certain distributions, symmetric distributions, as a rule, 95% of the cases differ from the mean by less than 2 standard deviations. Or 68% of the cases differ from the mean by less than 1 standard deviations. And more than 99% of the cases differ from the mean by less than 3 standard deviations. If we now consider the distribution of the number of heads obtained in 300 flips of a coin, we find that the probability of getting head between 133 and 168 is 95%. If we have the mean of the binomial distribution, which is for this case 150, and the standard deviation of the distribution, which is 8.66 for this example, we construct the interval for x as 150 minus 2 standard deviations, 2 times 8.66, and 150 plus, again we have a misprint in this formula. At the mid of here it should be less than x and less than 150 plus 2 times 8.66. Simplifying, we get the probability of x being between 133 and 167 is equal to 90%. Assuming that the above argument applies, therefore we can say that if a balanced coin is flipped 300 times, 90% of the time we will get anywhere from 133 to 167 heads. You may have noted that the described binomial distribution and other probability distributions by using Greek letters mu and sigma, which we reserved originally for populations. Indeed, statisticians often refer to binomial distributions as binomial populations. If a balanced coin is flipped, say, 100 times, the number of heads observed constitutes a sample of the results we might get if we repeated this experiment over and over again. The hypothetical population from which we are thus sampling consists of all possible experiments consisting of 100 flips of a balanced coin and it is characterized by the corresponding binomial distribution binomial distribution. Okay, this is the end of this lecture.